Welcome to the segment 4. In this segment, we'll talk about the data loader, how to feed the model for efficiency. Efficiency because the data will be prepared, will be pre-processed, will be sampled, will be made as batches, and then it will be given to the training process. So if you have already seen the training process in the training loop that we have just discussed in the previous segment, that in that particular training loop you need to feed the data, right, in terms of batches, right. So here you can see that for each epoch, right, so here we are running for 3 epochs, and you can see that for each epoch I am traversing through the entire data set by batch, right. And this is basically the data loader, which is defined here as the object, data loader object, which will automatically download or it will automatically prepare the data set for loading. Okay, so when we call the data set, this data set is essentially the preparation of the data itself from raw data to the pre-processed data, and then we'll transform and transfer the data to the loader, which will be used in your device for this entire training process. So essentially the data will be then transferred to the devices, and then your model will be running the forward pass, and then the loss function will be calculated, the backward pass will happen, and then the optimization or the update of the parameters will happen. So this is the standard training loop that we have seen. So what we were talking about data set is the contract to implement exactly 2 methods. Here you can see that len method and get item method. So these are the 2 main methods for your entire data set preparation, and PyTorch's data loader will call these functions automatically, so you do not need to call. So if we are making this custom data set or custom data loader, that means we need to prepare these 2 functions, and data loader will automatically call these 2 functions. Now what these 2 functions are doing, that's what exactly we are going to see. So what these 2 functions are doing here, you can see that here is one such minimal data set preparation for image classification, let's say. Now in this type of objective where we are doing the image classification, that means we need to prepare the image data set, right. If we are doing, for an example, NLP task, we need to prepare the natural language based or text based data set. So here you can see that this init process will automatically list the file paths, and it will get the list of the integer class IDs, and then the transformation will happen. So these are the tasks, the standard tasks we do in the init method, and this len and get item will be called automatically when we'll prepare or process the data loader. Okay, so in the training process or training loop, you have seen the data loader already, right. So that data loader was a data loader which is basically working on the already implemented init, len and get item method. So len and get item already has its pre-processed or already prepared data. Now here we are trying to get data from this designated path which we have initialized in the init method. So that means we are trying to access or give the data loader one custom data set, okay, which will be loaded from this path. So what this data set is doing, this data set is the key here, because it will get the data, prepare the data, and basically the data loader, which is basically the conveyor belt, which can run faster, which can run slower. Based on that, your entire process or training process will occur. Also if you are doing validation as. Now in this len will return the total number of samples in the data set. Let's say I have 100,000 of samples in the data set. So what is the length of this particular data set, that will be returned, and get item will traverse each index and basically return this particular sample So get item will return one pair of the input and the corresponding level, because we need the input and the level from the data, and that will be returned by get item one by one, right. So this is how the entire these two methods will work, and you can formulate your own custom len and get item method for your custom dataset. So this is one such example you are seeing for image classification, and here you are seeing another example for NLP task where we need this tokenized dataset, and you can see that this len is returning the number of samples that are there, which is the len function, and then get item is taking the item and is extracting the label. So basically it will, for that particular indexed label, it will get the item and it is returning the item. So what exactly I am returning here, that will be based on the custom function that I am making, and basically this will define the dataset preparation for the data loader. Now data loader constructor, here you can see the parameters. So the dataset object that we create, that dataset object will be the first argument here, and then you have the batch sizes, so samples per batch. So it will make or prepare the batch per worker. So essentially number of workers, you can see that this also we can define where this number of parallel workers will process for get item, because get item will fetch one by one sample and prepare that batch. And if we have 4 number of workers, so 4 such parallel workers will work on this get item method parallelly. Shuffle equal to true for training method or training process. We usually do shuffle equal to true because randomizing order is very important in training process. For validation, it is not required. Pin memory, so page locking, if we want to page lock CPU memory for faster GPU transfer, then we can do pin memory, so that pin memory will be true and it will transfer faster data. Drop last, because we may not have equivalent number of batches which we are creating here, so that final batch which is smaller than the batch size will be discarded if we make it true. Then we have the persistent workers equal to true. We will keep workers alive between different epochs. And prefetch factor equal to true. This will do the batches to preload per worker. So it will preload the workers and it will prefetch. So based on these parameters that we are defining or we are initializing, your entire data loader will work. Okay. So how data loader uses your data set? Sample, so there are several stages. Sampler will generate the shuffle list of indices, then batch sampler will group them into batches. So basically sampler will be the first process, and then batch sampler will work as the sub and basically make these batches. So they will group these indices into batches, and then the worker process will call dataset.getItem for each index item fetching in parallel, and workers will apply transforms. So if we need to do transform, because transformation is required for your what, if we want to do the raw data pre-processing, and virtually all the training process we see, we usually do pre-process, because no training process get raw data directly. Okay, we need to pre-process data. So that is the transformation process. We will see how it works, and then the assembling of tensors will happen, and then it will be placed into the shared memory based on what are the workers they are working. And then the main process will read the batches from the queue and yield them to the training loop, that loop we are seeing. So if we have, let's say, 100 samples and we are making batch size of 20, so that means in each epoch there will be 5 such iterations which will iterate through each batch, and those batches will be formed by this process, basically the data loader process, this conveyor belt that we are talking about. And this is how the iteration will happen for each epoch, and for each batch we are extracting the data and sending to the device, which is the GPU in training, most of the training cases, and if the GPU is not available, it will go to the CPU directly. So let's do some interactive study how this particular pipeline works. So to understand these workers, or how many workers are working and how they pipeline between the batch processing and the training, this loop happens, that we will see in this interactive session. Okay, so here you can see that first is the storage. Here we have the data, raw data we are having. Okay, we can have many different ways we can keep the storage. We can keep the storage in SSD, in HDFS, in NFS, based on where exactly the data stays. And then we have the sampler, right? So this sampler will sample, or it will generate the complete ordered list of integer indices for one epoch, right? This sampler, right? And sequential sampler will be used for validation, and if we do the shuffle, so that means, so 0, then maybe some random number will come, then random number, and then it will be grouped into these workers. So basically that is the exact thing we saw in the slide, and weighted random sampler will sample each sample has a weight, and over the sample rate it will have different ways to sample. Okay. There are distributed samplers as well, so we will talk about this when we will talk about the data distributed or data parallel training, okay, or distributed data parallel training. You have the batch sampler, so then it will wrap any sampler and groups indices into the list of batch size which is required for your each epoch loop inside this training loop, right? So each list will be sent to one worker. So you can see here we have worker 1 and we have worker 2, and your GPU training is happening. So it will initialize this init method, so this will be warming up, and in the same time we will do this worker processing. Okay, so this is basically happening as your worker 1, worker 2, and they are loading batch 1, batch 2, and they are preparing this batch. So basically they will be making, or the collating will happen. So essentially here you will have this worker get item and augmentation will happen, and then the collation will happen. So this collation once happens, that means my batch is ready to be sent to the GPU. So then your PCIe DMA will activate, and then batch will be sent to GPU. Now whether you are using that time your DMA or not, that will delay the process of the loading of the next batches. So that's why pin memory will be actually, and also several methods are there that we will see. But essentially what is happening here, batch is processed and then batch is sent to the GPU, and then you can see that training for batch 1 started, and similarly in the next loop you will have batch 2 and batch 3, 4, 5 and so on and so forth. Okay. So essentially your workers will process the parallel loading. So that means if you have persistence true, that means it will keep workers alive between these epochs, so that it will save at least 2 to 5 seconds startup per epoch, because workers will need to get initialized again. And prefetch factor, this will, each worker prefetches 2 batches ahead, so that in the next set of iterations it will be easier for the pipeline to get flushed. And similarly number of workers, obviously you can keep on increasing and see how much number of workers you can get per GPU. That means how many number of workers your CPU core will be supporting. Okay, usually maximum is equal to physical number of CPU cores per number of GPUs, because if you have 8 cores in your single GPU machine, that means maximum worker will be 8. That way you will be dividing the workers into each core for your data worker process, and then the collate will happen, and basically pin memory will enable faster GPU transfer, because in the normal CPU RAM, when it is pageable, the operating system can swap any page to disk at any time, because your other processes are running also. and this means the GPU cannot safely DMA direct from it. So that means this DMA transfer will happen just exactly after this process or collation happened. Your gate item finishes and your collate of all the data samples are there in the batch is ready, and your DMA will activate with the pin memory. Okay, so pin memory equal to true allocates the data loader output tensor directly in the pin memory, eliminating extra copy entirely. Okay, so that way you will accelerate your data loading process. Similarly, you have your shared memory. So basically workers cannot directly return these tensors because your raw data is transformed into your tensors, which will be basically going to your GPUs, right? But workers cannot directly return these tensors which were processed here to main process, because you will have each worker process sub boundaries. You cannot just send it. So instead they write this complete tensor batch to the shared memory, and then the main process maps it, and that's how it is happening. So how much shared memory you need? Number of workers into prefetch factor, because each worker will prefetch those many number of batches, into batch size, how many batch size per worker it is processing, obviously into the data size. So for image you have C into H into W, channel into height into width, per into bytes per pixel. So if you have 8 bytes per pixel or 1 byte per pixel, so based on that, this much shared memory you will have or you will need. Okay, so when we will talk about the next segment, acceleration, right, that time you will see that if your Docker has 64 MB as your default memory, which is shared memory, which will be enough for your one ImageNet batch with 4 workers. So if you increase the number of worker with your ImageNet batch, okay, so this memory will get increased and this will not fit into your shared memory. So that will basically slow down your data loading process also. But obviously this is very small compared to production grade real training. You can increase the size, so you can actually add your shared memory size, which is SHM size. Let's say 16 GB you can add, and you can restart your Docker, and basically you will have more shared memory per this shared memory for your data loading and shared across your workers. Once the batch tensor lands in the GPU memory, which is HBM for your let's say Hopper machines, the GPU will begin the forward pass, which we have seen as the training loop, at full tensor core throughput, because then we have all the data that is present inside my HBM. So I can throttle through this entire data and I can accelerate with my all streaming multiprocessors that are available. Okay, so that way I will increase the usability or the resource utilization for the GPU's streaming multiprocessors. Okay, so this is exactly how this will happen, and essentially you can measure the streaming multiprocessors usage and other things, and which are the parameters to set for each and every stage. That also we have talked about in the data loader constructor parameter setting. Okay, so transform will be happening for every raw data set. Transformation means obviously you will have different type of data which he will be working with for the training. So if I am working for image classification, I have image data. Now raw image data will be transformed. So there will be let's say here is the training transform for ImageNet data set. So for this we are getting the torch vision transforms. It has all these different algorithms for transforming your data. So like image clipping, image rotation, image flipping, you have jitter removal, all these different types of transformations you can apply, reshaping, resizing all the data based on what architecture that we are going to have, and based on that we can define these transform function. Okay, so this transform object will actually do the or this compose method will actually do the transformation, and you can see here the valid transformation will happen based on what type of resizing we are applying, what type of cropping we are applying for this image. So this is for image. Similarly, if you have any other data set for any other training, for that data set you have to do standard pre-processing. You have to also normalize the data, because you cannot send the raw pixel data. It will impact the gradient because it will be very unstable, and also the convergence will be fluctuating, so you will not get a stable training pipeline. So normalization is important. So that means there are many normalization methods. So we have to normalize so that the data stays between your average values, let's say between 0 to 1, right? So raw value to the normalized value, that will actually have the training process expedited, and also the gradients will be stable throughout this training process. So this is basically the transformation plus normalization. And also if you need to have augmentation, that means addition of new data, so cropping, resizing, then cropping, adding, so all these different transformation will happen, and basically this constitutes the transform stage, where you are transforming from raw data to the actual input of the data set that you are going to need for the training process. So the bottlenecks, we talked about that. So number of workers, usually we start with 0 and then we increase and see how the performance is happening, or it is scaling. If we initially give too many number of workers, it will explode. So we usually start with a small number of workers, and also we study the GPU utilization to see how the SMs are utilized, and based on that also pin memory through giving at least 1.2 to 1.5 times speed up will give, because the pageable memory will be pinned and they will no longer be used. So your DMA can just start on the memory directly, DMA transfer. Now here the gate item alone will actually be working as a data loader, right? So if this is slow, storage is the bottleneck, because your data is not getting processed. If this is fast, so that means collation or worker communication is slow. So that means your pre-processing is getting fast, but your worker communication is not getting synchronized, so collation is not happening. So basically gathering all the batches by the worker sub process, which will be sent to your shared memory, and from there you will have the transfer to the GPU. So this isolation of IO versus the pre-processing is also needed. Okay, and dummy data loader also is another trick. We usually replace our dataset with fast in memory synthetic dataset, and if training suddenly reaches around 95% utilization, then the real dataset is basically the bottleneck. So we usually see how much let's say dummy data we can keep. If dummy dataset makes GPU utilization jump to 95%, then we can understand that your real dataset pre-processing is the bottleneck, because it is already in the memory, right? Your synthetic dataset. So so my GPU utilization is achieving 95%. That means there is a chance to improve the data pre-processing, so that for the real dataset it reaches to 95% and close towards the 100%. So that means the real dataset pre-processing will be bottleneck if my dummy dataset makes 95% utilization. Otherwise there are problem elsewhere, right? Where it is the bottleneck, the model is the bottleneck or the GPU is the bottleneck. If with the dummy dataset you are not reaching to 95% utilization. Okay. So in summary, we have the dataset and data loader. So dataset, we have the we can write a dataset by subclassing this and implementing the lem and gate item, and the data loader will call them automatically when we'll do the data loading. And the data loader will have different parameters, and what they do we have talked about. what are the bottlenecks in the training process in terms of data transfer and pre-processing, that also talked about, and also the utilization in terms of streaming multiprocessors or GPU streaming multiprocessor utilization. If it is not reaching to 90 or 95%, where exactly is the bottleneck, that also we know now with the synthetic dataset training and utilizing the GPU bottleneck. Okay. So thank you, and we'll in the next session we will see how to expedite further the process with the different precision. Okay. Thank you.